Given that we're working with STL files, selection of faces can be a bit of a problem, but in ParetoWin, we will see what features are available to overcome this challenge. To begin with, let's load the STL model, which is the edge cantilever problem. And once we load this model, you'll notice that it has lots of smooth edges or fillets that will make the selection of faces a bit of a challenge. Now what we'll do is we'll start with the default material of alloy steel. Then for boundary conditions, we'll select the back face, which is fairly easy to pick because it has sharp edges, and we will set the boundary condition to be fixed in all directions, and we apply. That is easy. Now what we'd like to do is we'd like to pick a subset of this face, and the STL file, if you go to the display mode and look at the wireframe, you'll notice that there is a subset of this face consisting of these two triangles that we would like to pick in order to apply a force. Now if you go to the default mode under boundary conditions and try and pick this face, of course it'll pick all the triangles that are connected to it until it hits a sharp edge. That's not what we want. So what we'd like to do is pick just two triangles, and to do that we change the face type to triangle, and now pick the first triangle, hold the control key, and pick the next triangle. So now we've selected a subset of triangles, and now we can apply whatever boundary condition we would like. So we can apply a force of minus 5,000 or 5,000 newtons in the negative y direction, and we apply. The next problem we like to solve is to pick the planar face, just the planar portion of the top face. And as expected, we have the plane option, and this picks triangles that make up a plane. So you can pick anywhere on this plane, and it picks the portion that makes up a plane and does not go beyond the planar portion. And now we can apply, say for example, a pressure loading of 10,000 pascals on the top. And the last boundary condition I'd like to apply is we'd like to retain the subset of the cylinder without the fillets, just the internal portion. And to do that, this is a very fine cylinder, so we'd like to make that into a cylinder, and we pick anywhere in that cylinder, and it picks pretty much most of the triangles here. And since the edges are jagged, it's not very clean, but because of the retained surface, it's not that critical. So we're going to go ahead and retain that face, and we are done. So that kind of illustrates the subset of triangle selection, the planar selection, and the fine cylinder selection, how they can be helpful in applying boundary conditions on an STL model. With all that out of the way, we can go ahead and carry out an FEA with a medium mesh quality. And once we complete the FEA, we'll move on to topology optimization. For topology optimization, we will remove as much material as possible. We'd also like to impose a draw direction of Z, which essentially says do not have any cavities along the thickness direction. Also impose symmetry along the thickness direction. With those options, we'll optimize. And the optimization will take a little bit to complete. The optimization is complete, and you'll notice that it has met all the constraints that we imposed. It has retained the cylindrical face, and in fact has also retained the top planar surface so that it can apply a pressure load, and it has retained this corner edge where we applied a force. And you'll also notice that once we scroll through the topologies, each of these designs meets all the design constraints you imposed. The faces are retained, the pressure load face is retained, and so is this face here. And that's an important point to note, is that every design that we get meets all the performance and design constraints that we impose. That concludes the video on how one can select subfaces in ParetoWin.